NENOMATICA, where mathematics meets YouTube excellence. Exponential Inequalities. Welcome to our mathematics video. Today, we're going to learn how to solve exponential inequalities of the form a to the power of f of x is greater than or equal to b. Let's focus on solving inequalities of this form. We need to solve this inequality under the following conditions. B is greater than 0, a is not equal to 1, and is greater than 0. The key insight for solving exponential inequalities is that we can often take logarithms of both sides, as long as we're careful about the conditions and whether we need to flip the inequality sign. When b is greater than 0, a is greater than 0, and is not equal to 1, we can take logarithms of both sides to solve for f of x. Let's consider two cases. First, when a is greater than 1. In this case, taking the logarithm with base a preserves the inequality direction. Now, let's consider the second case, when it is between 0 and 1, excluding 1. In this case, the logarithm with base a is a decreasing function, so we need to flip the inequality sign. Now, let's discuss a special case mentioned in the problem. When b is less than or equal to 0, the inequality a to the power of f of x is greater than or equal to b holds for every x in the domain of definition. This is because for positive values of a to any power is always positive, and any positive number is greater than any non-positive number. Additionally, it's important to note that the inequality a to the power of f of x is less than or equal to b has no solution when b is less than or equal to 0 and is not equal to 1 and it is greater than 0. This is because a to any power will always be positive, so it can never be less than or equal to a non-positive number. Let's solve an example to make this concept clearer. Find the values of x that satisfy 2 to the power of x squared plus 1 is greater than or equal to 8. In this example, a equals 2, which is greater than 1. So we're in the first case we discussed. We can take the logarithm with base 2 of both sides. Simplifying the left side, we get x squared plus 1 is greater than or equal to log base 2 of 8. We know that log base 2 of 8 equals 3. So our inequality becomes x squared plus 1 is greater than or equal to 3. Subtracting 1 from both sides, we get x squared is greater than or equal to 2. Taking the square root of both sides, and remembering that when we take the square root of both sides of an inequality, we need to consider both positive and negative values. We get x is less than or equal to negative square root of 2, or x is greater than or equal to square root of 2. Let's solve one more example. Find the values of x that satisfy the inequality. 1/2 to the power of 2x minus 3 is greater than or equal to 1/4. In this example, a equals 1/2, which is between 0 and 1. So we're in the second case we discussed. We'll take the logarithm with base 1/2 of both sides. But remember that we need to flip the inequality sign because logarithm with base less than 1 is a decreasing function. Simplifying the left side, we get 2x minus 3 is less than or equal to log base 1/2 of 1/4. We know that log base 1/2 of 1/4 equals 2 because 1/2 squared equals 1/4. So our inequality becomes 2x minus 3 is less than or equal to 2. Adding 3 to both sides, we get 2x is less than or equal to 5. Dividing both sides by 2, we get x is less than or equal to 5/2. Let's start by looking at the example we need to solve. We have 3 raised to the power of 2x minus 1, which is less than 11 raised to the power of 3 minus x. When solving exponential inequalities, a key strategy is to apply logarithms to both sides. We can use any logarithm base, but it's convenient to use the same base as one of the exponentials. Let's take the logarithm with base 3 of both sides. Next, we can use the power property of logarithms, which states that the logarithm of a power equals the exponent times the logarithm of the base. So we get 2x minus 1 times log base 3 of 3, which is less than 3 minus x times log base 3 of 11. Since log base 3 of 3 equals 1, we can simplify the left side. So we have 2x minus 1 is less than 3 minus x times log base 3 of 11. Now, let's expand the right side by distributing the log base 3 of 11. This gives us 2x minus 1 is less than 3 times log base 3 of 11 minus x times log base 3 of 11. Our next step is to rearrange the inequality to get all terms with x on the left side. We add x times log base 3 of 11 to both sides, and add 1 to both sides. This gives us 2x plus x times log base 3 of 11 is less than 1 plus 3 times log base 3 of 11. Now we can factor out x on the left side. So we have x times the quantity 2 plus log base 3 of 11 is less than 1 plus 3 times log base 3 of 11. Finally, to isolate x, we divide both sides by the quantity 2 plus log base 3 of 11. Since this quantity is positive, as log base 3 of 11 is positive, the inequality direction doesn't change. This gives us x is less than the fraction with numerator 1 plus 3 times log base 3 of 11, and denominator 2 plus log base 3 of 11. Therefore, the solution set D is the interval from negative infinity to this fraction. Let's review the key steps in solving this exponential inequality. First, we took logarithms of both sides using base 3. Then we applied the power property of logarithms to bring down the exponents. We simplified the expression by using the fact that log base 3 of 3 equals 1. Next, we expanded the right side and rearranged to get all terms with x on the left. Finally, we factored out x and divided both sides to isolate x. Conceptually, what we've done is convert an exponential inequality into a linear inequality by using logarithms. This is a powerful technique that works because logarithms maintain the order of inequalities for positive numbers. Let's explore how to approach this type of problem with a clear method. Let's look at our example. We need to solve the inequality. 1 is less than 3 raised to the absolute value of x squared minus x, which is less than 9. To solve this inequality, our first step is to take the logarithm base 3 of all sides. This will help us isolate the exponent. Now, we can simplify these logarithms. The logarithm base 3 of 1 is 0. For the middle term, we can use the property that the logarithm of a power equals the exponent times the logarithm of the base. So, log base 3 of 3 raised to absolute value of x squared minus x equals absolute value of x squared minus x times log base 3 of 3. For the right side, log base 3 of 9 equals log base 3 of 3 squared, which equals 2 times log base 3 of 3. The logarithm base 3 of 3 is 1, so our expression simplifies further. We need to be careful about the values where x squared minus x equals 0, because these would make 3 raised to the power of 0, which equals 1. This would violate our original inequality, which strictly states that 1 is less than the expression. So we solve x squared minus x equals 0 by factoring out x, giving us x times quantity x minus 1 equals 0, which means x equals 0 or x equals 1. We need to exclude these values. Now, let's focus on solving the absolute value inequality. Absolute value of x squared minus x is less than 2. For an absolute value inequality of this form, we can rewrite it as a double inequality. So we have negative 2 is less than x squared minus x, which is less than 2. Now, we'll solve each part of this double inequality separately. First, let's tackle the left part by adding 2 to both sides. X squared minus x minus 2 is less than 0. This is a quadratic inequality. We can factor it as quantity x plus 1 times quantity x minus 2 is less than 0. When we solve this inequality, we find that x is between negative 1 and 2, so negative 1 is less than x, which is less than 2. For the second inequality, x squared minus x plus 2 is greater than 0, we can determine that this inequality is always true for all real numbers, because a quadratic with a positive leading coefficient and a positive constant term can't be negative. So this tells us that x belongs to the set of all real numbers. Now, we need to combine our results. From the quadratic inequalities, we found that x is in the interval from negative 1 to 2. But remember, we also need to exclude the values x equals 0 and x equals 1. Therefore, the solution set D equals the open interval from negative 1 to 2 minus the set containing 0 and 1. Let's look at our example. We need to solve the inequality. The square root of 9 over 10 multiplied by 9 over 10 raised to the power of x minus 1 is greater than 10 to the power of 3/4 x minus 1, all over square root of 10. This is a complex exponential inequality, but we'll solve it systematically using properties of logarithms and algebraic manipulation. The first step when solving exponential inequalities is to take the logarithm of both sides. Since logarithm is an increasing function, it preserves the inequality direction. So we take the logarithm of both sides of our inequality. Next, we'll use the properties of logarithms to simplify our expression. Specifically, we'll use three key properties. First, the logarithm of a product equals the sum of logarithms. Second, the logarithm of a quotient equals the difference of logarithms. And third, the logarithm of a power equals the power times the logarithm. Applying these properties, we get log of square root of 9 over 10 plus log of 9 over 10 to the power of x minus 1 is greater than log of 10 to the power of 3/4 x minus 1 minus log of square root of 10. This allows us to work with the exponents more directly. Now, let's apply the power property of logarithms to the terms with exponents. For the square roots, we use the fact that square root is the same as raising to the power of 1/2. This gives us log of 9 over 10 to the power of 1/2 plus x minus 1 times log of 9 over 10 is greater than 3/4 x minus 1 times log of 10 minus 1/2 times log of 10. We're making good progress in simplifying our inequality. Let's further simplify this expression. We know that log of 10 is equal to 1 because 10 to the power of 1 equals 10. Therefore, our inequality simplifies to x minus 1 times log of 9 over 10 plus 1/2 times log of 9 over 10 is greater than 3/4 x minus 1 times 1 minus 1/2. This simplifies to x minus 1 times log of 9 over 10 plus 1/2 times log of 9 over 10 is greater than 3/4 x minus 1 minus 1/2. Now, let's expand the left side of our inequality to group-like terms. We get x times log of 9 over 10 minus log of 9 over 10 plus 1/2 times log of 9 over 10 is greater than 3/4 x minus 3/2. We're continuing to reorganize our expression to isolate the variable x. Let's rearrange our inequality to isolate terms containing x on one side. We move the term 3/4 x to the left side, and we move all terms without x to the right side. This gives us x times log of 9 over 10 minus 3/4 x is greater than log of 9 over 10 minus 1/2 times log of 9 over 10 minus 3/2. We're getting closer to our solution by isolating x. Now, let's factor out x on the left side of the inequality. We get x times the quantity log of 9 over 10 minus 3/4 is greater than negative 3/2 plus 1/2 times log of 9 over 10. This is an important step as we're now close to solving for x. To isolate x, we need to divide both sides by the coefficient of x. However, since log of 9 over 10 is negative, and we can verify that log of 9 over 10 minus 3/4 is also negative, dividing by a negative number reverses the inequality sign. Therefore, our final solution is x is less than negative 3/2 plus 1/2 times log of 9 over 10, all divided by log of 9 over 10 minus 3/4. This gives us the solution set for our exponential inequality. In conclusion, we've solved this exponential inequality by, first, taking the logarithm of both sides to handle the exponential terms. Second, using logarithm properties to simplify the expression. Third, rearranging terms to isolate the variable x. And finally, solving for x while being careful about the direction of the inequality when dividing by a negative number. This approach can be applied to many types of exponential inequalities. Thanks for watching. Let's solve the following exponential inequality. We have 5 raised to the power of 1/4 times the logarithm base 5 of x squared is greater than or equal to 5x raised to the power of 1/5 times the logarithm base 5 of x, where x is greater than 0. This is a complex inequality involving both exponential and logarithmic terms, so we'll need to apply several properties to solve it. Our first step is to take the logarithm base 5 of both sides of the inequality. Since logarithm is an increasing function, this doesn't change the direction of the inequality, so we apply logarithm base 5 to both sides. Now, we'll simplify both sides by applying the logarithm property that the logarithm of a power equals the exponent times the logarithm of the base. For the left side, the logarithm base 5 of 5 raised to some power is simply that power. So the left side becomes 1/4 times the logarithm base 5 of x squared. For the right side, we can rewrite it as the logarithm of a product, which equals the sum of the logarithms. So we get the logarithm base 5 of 5, plus the logarithm of x raised to the power of 1/5 times log base 5 of x. Let's continue simplifying. The logarithm base 5 of 5 is just 1, because 5 to the power of 1 equals 5. For the term on the right, we again use the power property of logarithms. The logarithm of x raised to the power of 1/5 times log base 5 of x equals 1/5 times log base 5 of x squared. To solve this inequality, let's rearrange terms to get all variable terms on one side and constants on the other side. We'll subtract 1/5 times the logarithm base 5 of x squared from both sides, and we'll also subtract 1 from both sides. Now, we can combine the like terms on the left side. We have 1/4 minus 1/5 of the logarithm base 5 of x squared. Let's calculate this fraction. 1/4 minus 1/5 equals 5 over 20 minus 4 over 20, which simplifies to 1 over 20. So we have 1 over 20 times the logarithm base 5 of x squared is greater than or equal to 1. Let's multiply both sides by 20 to simplify the coefficient. This gives us the logarithm base 5 of x squared is greater than or equal to 20. Now, we can take the square root of both sides. When taking the square root of an inequality, we need to consider that the logarithm could be positive or negative, so we need the absolute value of the logarithm base 5 of x. This gives us the absolute value of logarithm base 5 of x is greater than or equal to the square root of 20, which is approximately 2 times the square root of 5. To resolve the absolute value, we need to split this into two cases. Case 1. Logarithm base 5 of x is greater than or equal to 2 square root of 5. Case 2. Logarithm base 5 of x is less than or equal to negative 2 square root of 5. Let's solve each case. For case 1, if logarithm base 5 of x is greater than or equal to 2 square root of 5, then x is greater than or equal to 5 raised to the power of 2 square root of 5. For case 2, if logarithm base 5 of x is less than or equal to negative 2 square root of 5, then since logarithm is a strictly increasing function, we get x is less than or equal to 5 raised to the power of negative 2 square root of 5. But we also need to remember our original constraint, that x must be greater than 0. Therefore, the solution set is x is in the interval from 0 to 5 raised to the power of negative 2 square root of 5, in union with the interval from 5 raised to the power of 2 square root of 5 to positive infinity. To visualize this solution, imagine a number line where we've excluded all values between 5 to the power of negative 2 square root 5 and 5 to the power of 2 square root 5. This example demonstrates the power of logarithmic properties when solving exponential inequalities. The key steps we used were: 1. Taking logarithms of both sides to simplify the exponential expressions. 2. Using logarithm properties to simplify complex expressions. 3. Combining like terms to create a quadratic inequality. 4. Applying absolute value rules to split the solution into two cases. 5. Translating back from logarithmic to exponential form for the final answer. Remember that whenever you have an inequality with exponential expressions, taking logarithms is often a good first step to simplify the problem. Welcome to this tutorial on solving exponential inequalities. Let's look at an example. To solve this exponential inequality, we need to start by taking the logarithm of both sides. This is a common approach for solving exponential inequalities because it allows us to bring down the exponent. Next, we apply the logarithm power rule, which states that the logarithm of a number raised to a power equals the power times the logarithm of the number. So we get x squared minus 6x plus 8 times log of x minus 2 is greater than 0. Note that log of 1 equals 0, which simplifies our right side. Now we have a product of two factors that is greater than 0. For a product to be greater than 0, either both factors are positive or both factors are negative. Let's analyze these cases separately. Case 1. Both factors are positive. First, let's consider the quadratic factor, x squared minus 6x plus 8. We can factor this as x minus 4 times x minus 2, which gives us that x is less than 2 or x is greater than 4 for this factor to be positive. For the logarithmic factor, log of x minus 2, to be positive, we need x minus 2 to be greater than 1, which means x greater than 3. Combining these conditions and considering our domain restriction that x is greater than 2, we get that x must be greater than 4 for the first case. Case 2, both factors are negative. For the quadratic factor to be negative, x must be between 2 and 4. For the logarithmic factor to be negative, x minus 2 must be between 0 and 1, which means x is between 2 and 3. Combining these, we get that x must be between 2 and 3 for the second case. Now, we need to combine the results from both cases to get our final answer. From case 1, we have x greater than 4. From case 2, we have x between 2 and 3. Taking the union of these intervals, our final answer is x is in the interval from 2 to 3, union with the interval from 4 to infinity. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.